In this video, we're going to prove that the additive and multiplicative identities of the integers are unique. So let's recall a couple definitions. First, the definition of an additive identity. An additive identity in a number system S with an operation of addition is an element z in the number system such that for all n in the number system, n plus z equals z plus n equals n. Okay, so that's the sort of formal definition of an additive identity. Now, one of the axioms in our definition of the integers is the statement that there is an additive identity. So we take the existence of an additive identity as a given in the integers. But of course, this axiom doesn't state everything. We know that 0 is the additive identity. We know that when you add 0 to anything, you get that same thing back. And we know that that's the only number that has that property. But in this course, we're not going to start with what we believe we know about the integers. We're not starting with the objects that we're familiar with, the numbers. We're starting with axioms, and we're going to use those axioms to define the objects and to define what their behaviors are. Okay, so here we're going to prove that there's only one additive identity in Z, and then we'll give it the special name of 0. So here's our theorem. The additive identity of Z is unique. So to prove this, we're going to do a direct uniqueness proof. So a direct uniqueness proof starts by assuming that you have one thing of the type and another thing of the type, and then you prove that they're equal. So we're going to prove that if 0 is an additive identity and Z is an additive identity, then 0 is equal to Z. So let's assume that 0 is an additive identity. And let's assume that Z is an additive identity. Well, using the fact that Z is an additive identity, using the fact that 0 is an additive identity, we know that if we add 0 to anything, we get that same thing back. So we know that 0 plus Z has to be Z. All right? Now, on the other hand, Z is an additive identity. So if we add that to anything, we get the same thing back. So 0 plus Z is also going to be 0. But the sum of two integers is unique. So we know that 0 plus Z, even if it has an outcome with two different names, has to have the same value. So 0 is equal to Z. All right, so that proves that the additive identity of the integers is unique, and from here on out we can refer to it as 0. Now we have another axiom of the integers that's important to mention here, and we stated it originally as follows: if m and n are integers, and the product of m and n is equal to an additive identity, then one of those numbers, m or n, possibly both, is equal to an additive identity. All right. Now, additive identity, of course, we just declared there's only one of them, and we called it 0. So we can restate this axiom in a little bit more sensible way. If m and n are integers and their product is 0, then m or n is 0. Okay? And we refer to this axiom by stating that Z has no 0 divisors, or there are no divisors of 0 in Z. So let's look at multiplicative identities. Okay, so a multiplicative identity in a number system S with an operation of multiplication is an element U in the number system such that for all n in S, n times U is equal to U times n is equal to n. All right, so it operates a lot like what we know 1 does when you multiply by it. And one of our axioms in the definition of the integers is a statement that there is a multiplicative identity in the integers. But of course, this axiom doesn't state everything. Again, we know that 1 is the one and only multiplicative identity in the integers. But again, in this course, we're not starting with the objects that we know and love. We're not starting with the integers. We start with axioms that define the number system. And those axioms define the objects in the number system and define their behaviors. Okay? So here we're going to go ahead and prove that there is only one multiplicative identity in the integers, and then we'll give it a special name. We'll call it 1 like we'd like to. So here's our theorem. The multiplicative identity of Z is unique. The proof is very similar to the uniqueness proof of the additive identity. Let's assume that 1 and Z are both multiplicative identities of the integers. Well, since Z is a multiplicative identity, when we multiply it by 1, we're going to get 1 back. And since 1 is a multiplicative identity, when we multiply it by Z, we're going to get Z back. Okay? And again, 1 equals z then, because the outcome of multiplication is unique. So 1 times z, regardless if it has two different names, has got to have the same value, so 1 is equal to z. So we've just proven that a multiplicative identity has to be unique in the integers. So we'll call it 1 again. Now there's one more axiom of the integers that we should mention here. We have an axiom that states that the additive identity and the multiplicative identity are not equal. Okay, so now that we know that the additive identity and the multiplicative identities are unique, and we've given them the names 0 and 1, then we can restate this axiom as 0 is not equal to 1. Okay, so we're taking that as an axiom, 0 is not equal to 1. That's a little bit odd. It's worthwhile to think about why we need to have the statement 0 is not equal to 1 as an axiom. Okay, again, although we believe that we know that 0 is not equal to 1, we can't rely on that fact. We either have to prove that it's true or do what we do here and take it as an axiom. So we're using our axioms to define the number system. Okay, and of course a number system that results from our axiomatic development should match our intuition. So we better either have as a result or an axiom that 0 is not equal to 1, because that sure as heck is a part of the integers as we know them, right? So it's worthwhile to think about, though, what would our number system look like if we didn't declare that 0 is not equal to 1? And sort of as a process for thinking about this, look at the other axioms. If we didn't declare that 0 is not equal to 1, if we allowed 0 is equal to 1, what would happen to the integers? They'd look a lot different. And I think you'll find after you think about it for a while, they'd be a lot less useful. So that's it for this video. Thanks for listening.